So we've been solving systems of equations, of linear equations, and remember what that means is we are looking for a point that works in both equations. So the one method that we used was solving by graphing. And so we would look where those points, where those lines would intersect, because that is a point that both lines have in common, so it is the solution to the system. Now, graphing works well because most of us know how to graph really well. However, what if the numbers are very large? Or what if we have decimals or fractions that are difficult to graph or difficult to read on the graph? So we have to have other methods for solving a system of linear equations. So the next method we're going to use is substitution. Okay, so substitution is a method that's used for solving systems that works better than graphing with large numbers, fractions, or decimals. Now, remember, as I just said, a solution to a system is a point that works, an ordered pair that works in both equations. Okay, so if this new method is called substitution, what does substitution mean? It means to replace. So let's just do a very simple example. This is not a system. I just said substitute x equals -2 into this linear equation. So if I put in -2, which means I'm replacing x with -2, substitution means to replace, I get 16 plus 3 is 19. Okay, so what would that mean? Well, this is just a line, and -2, 19 would be a point on that line. But the point of that was to remind you that substitution means we are replacing the variable with this number. Okay, so let's take a look here at the first example. We have y equals 15 minus x, and we have 4x plus 3y equals 38. So we can tell by these large numbers that graphing wouldn't work very well. So we have another approach, substitution. So the key for this is to use substitution. You want to get one of the equations, you want to get a variable by itself. So let's take a look here. Well, do you see in the first equation y is already by itself? So that's a good thing. So what we are going to do now, since y equals 15 minus x, we're going to take 15 minus x and we are going to substitute it in for y into the other equation. In other words, we are going to replace y with 15 minus x. So, why do we do that? Well, let's take a look here. So my second equation is 4x plus 3, but I'm no longer putting y in, I'm putting 15 minus x in for y. That's what y equals, and equals 38. Now, do you notice I have an equation and we have all one variable, everything in x, which means I can find the x coordinate. So if I distribute, I get 4x plus 45 minus 3x equals 38. Combine like terms, subtract 45, and I have x equals -7. Now, you have to keep in mind what we're doing. We're solving a system, and the answer to a system is a point. Well, x is the x coordinate of that point, so we're not finished. This is called substitution because you actually have to do this twice. Meaning you have to substitute again. I need to find the y coordinate. -7 is my x coordinate of the point. I need to find the y coordinate. So I'm going to go back up to the equation. I could replace and put x in either one of these because this is an x that works in either one. However, I always tend to go to the equation that I used for substitution. I didn't circle it, but sometimes I circle that to remind myself that's my main equation I'm going to be using. Okay, so if I put in -7 here, I get 15 minus -7, so I get y is 22. So if we would have graphed these two lines, which meant we would have had to have a very large graph, they would have intersected at the point -7, 22. Okay, now let's go to the example in the notes below that one. The one where we have x equals y plus 2 and 2y plus x equals 17. Now, remember what I said. I know that we are brainwashed that get y by itself, get y by itself, get y by itself. We do that so that if we're graphing, we get lines into slope-intercept form. We get y by itself, so we have y equals mx plus b. Okay, we're not graphing. This is something else. We are solving a system, and the key is being able to take one of the equations and substitute it into the other. So in this example, x is by itself, and that's okay. I'm not graphing this. X is equal to y plus 2. So what I'm going to do now is I'm going to replace x in the other equation with y plus 2. So I have 2y plus, but instead of x, I'm going to substitute or replace it with y plus 2 because that's what x equals in that equation, equals 17. I just put that in parentheses to show you that I replaced it with y plus 2. Now, do you see why we do this replacement? Look at this equation. Don't we have it down to one variable, y? So now we can solve that equation. Like terms, so I have 3y plus 2 is 17. Subtract 2 and I get 15. Divide by 3 and I get 5. We are not finished. This is the y-coordinate of the point where they intersect. So now I've got to find the other coordinate, the x-coordinate. Well, we substitute again. I could put 5 into either one of these. However, I find it's just as easy to go back to that original equation I worked with. Okay, put in 5 for y, x equals 5 plus 2, so x equals 7. So these two lines would have intersected at 7, 5 if we had graphed it. This is an answer that works in both. Let's check it. If I put in 7 for x and 5 for y, 5 plus 2 is 7, 7 equals 7. Yep, that's true. If I put in 7 for x and 5 for y, I get 10 plus 7, which is 17. That works. Okay, let's go to the next example that is on the right side of this one. Y equals 3x and x plus y equals 8. All right, so the key is having an equation with a variable on a side by itself. Well, I already have that one. So I'm going to replace y in the other with 3x. Since I already have an equation with a variable by itself, that's the one I'm going to work with. So I have x plus, but instead of y, I'm going to replace it or substitute it with 3x equals 8. And again, why do we do that? Oh, now we have a nice equation in terms of one variable, and I can solve for that variable. I add like terms, and I get x is 2. Now, we are not finished because the answer to a system is a point. This is the x-coordinate of the point. Now I've got to find the y-coordinate. So I can put 2 in for x. It doesn't matter where. I could put it here. I could put it here because this is an x that works in both. I always tend to go back up to the equation that I use for substitution. Again, you may want to circle that. So 3 times 2 is 6. Showed it down here. So 2, 6 is the answer to the system. Easy to check on this one. 3 times 2 is 6. 2 plus 6 is 8. Now, if you're thinking, oh, that would have been easy to graph, I agree with you. I'm just starting out with, I guess, would say easier problems on our first day of substitution. Okay, now let's take a look at the last one. I have 2x plus y equals 9 and x plus 4y equals -1. All right, so far in the other 3 examples, one of the equations had a variable already by itself. All right, that doesn't mean we can't do that. That just means that we have to rearrange one of the equations to get a variable by itself. So the key is, in this problem, I'm going to look for what's going to be the easiest variable to get by itself. Well, in the red one, I could get y by itself, couldn't I, if I subtracted 2x? In the black one, I could get x by itself if I subtracted 4y. So I have 2 choices here. But the key is, when you start a problem and you don't have a variable already by itself, the key is looking for one of the variables that has a coefficient of 1. Remember, that's like a ghost, or there's no other number outside of it. It really has a coefficient of 1. So for no particular reason, I went ahead and decided to get y by itself, which means I got to subtract 2x. Now, I could have written this as -2x plus 9. That's fine. Now, I'm going to go into my other equation, and I'm going to replace or substitute y with 9 minus 2x or -2x plus 9. So here I go. So I have x plus 4, but instead of y, I'm going to replace it or substitute it with 9 minus 2x, or negative 2x plus 9 equals negative 1. Again, why do we do that? Oh, now I have an equation all in terms of x, or one variable. I can solve for x. So I'm going to distribute. So I have x plus 36 minus 8x equals negative 1. I'm going to put my like terms together. X minus 8x is negative 7x, plus 36 equals negative 1. I'm going to subtract 36, which gives me a negative 37. And then I'm going to divide by negative 7, and I have 37 sevenths. Doesn't mean I made a mistake because I got a fraction. No. All right, as I did in the first example, I showed you we got a large answer, which wouldn't have worked very well with graphing. The other two, graphing or substitution, would have worked. This problem, it's pretty obvious that graphing, you're not going to be able to read a graph and say, oh, the answer is 37 sevenths or 5 2/7. Okay, we're not finished. That's the x-coordinate. Remember, no fear of fractions. Now we got to replace, we got to find y. So I got to take 37 sevenths and put that in for x. Again, I could put it in any of these, but I would, if I were you, the variable, the equation that you had the variable by itself, I would circle that, and that's the one that you use for substitution. In the beginning and in the end, we're going to replace x with 37 sevenths. So y is 9 minus 2 times 37 sevenths. All I'm going to do is multiply 2 times 37, and that is 74. So I have 9 minus 74 sevenths. Now, I need a common denominator. Well, I already have a 7 here, so I didn't show that, but if I had 9 over 1, I would have multiplied by 7 over 7, or got 63 sevenths. Isn't 63 divided by 7 equal to 9? Common denominator, so now I take 63 minus 74, and I get negative 11 sevenths. So substitution is our second way of solving equations. The idea is to isolate a variable, get one variable and a side by itself, and replace that expression into the other variable. Your answer is a point.